Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Spherical Coordinates and Triple Integrals. As always, please be an active learner as you watch this video. By way of introduction to triple integrals in spherical coordinates, another useful coordinate system in 3 dimensions is the spherical coordinate system. It simplifies the evaluation of triple integrals over regions bounded by spheres or cones. The spherical coordinates, rho, theta, and phi, it's an ordered triple, of a point P in space are shown below. Notice that rho is the distance between 0 and the point P, the distance from the origin to point P. Theta is the same angle as in cylindrical coordinates, and in polar coordinates for that matter. It goes from the positive x-axis and it goes counterclockwise. And phi is the angle from the positive z-axis in the line segment OP. Note that rho is bigger than or equal to 0, and phi is between 0 and pi inclusive. The spherical coordinate system is especially useful in problems where there is symmetry about a point, and the origin is placed at that point of symmetry. For example, the sphere with center, the origin, and radius c has a simple equation, rho equals c, and we can see that here. So if you get rho equals c, you say this radius is a constant for all that, so that means you have a sphere. The graph of theta equal a constant says this angle is always constant. That's going to be a half plane. And the graph of phi equal a constant, meaning this is always constant as you go around. The others can vary all the way. You will get a cone. This is the cone you get if c is between 0 and pi over 2. And this is the cone you will get if you're between pi over 2 and pi. The relationship between rectangular and spherical coordinates can be seen from the figure below, and I'm calling that figure 5 here. So this is the picture we're referring to. Now z is the distance from here to here, and if you just look at the right triangle that you have and notice that this is a 90-degree angle, you can conclude that z, this direction, is rho cosine phi. And if you look at the fact that this segment is the same as that segment, you can conclude that r is equal to rho sine phi. But then we can use the fact that we know that x is r cosine theta, so we will substitute in what we have for r. There's r cosine theta using this r, so we get x is equal to rho sine phi cosine theta, and similarly y is equal to r sine theta, so this is r rho sine phi times sine theta, and then z is as before. So we now have x, y, and z in terms of rho, phi, and theta. And we also have that rho squared is equal to x squared plus y squared plus z squared by the distance formula. So these are the equations that we use to employ spherical coordinates. Let's practice that with a problem. The point 2, pi over 4, pi over 3 is given in spherical coordinates. And by the way, someone has to tell you what this coordinate is given in, but it's given in spherical coordinates. Plot this point and find its rectangular coordinates. You know what to do. Let's see how you did. Okay, so in spherical coordinates, we use the conversion factors that we have. So we know that rho is 2. We know that phi was pi over 3, and we know that theta was pi over 4. And so we get this for x. We substitute those values in, do the calculation, we get this. Similar for y and similarly for z. And if I were to plot this point, I would go out in the x direction, square root of 3 over 2. And in both the x and y, and then I would go up 1. And so these are the coordinates that you should get in rectangular coordinates. Let's practice going the other way. This point, 0 to square root of 3 minus 2, is given in rectangular coordinates. Find the spherical coordinates for this point. You know what to do. Let's see how you did. Okay, so we're starting with those points in rectangular coordinates. First thing probably to do is to find rho. So rho is going to be the sum of the squares of the x, y, and z coordinates. I square each of those. And when you square 2 square root of 3, of course, you get 12 plus 4, and that is the square root of 16, which is 4. Now we have to go after the angles. Well, we know that z is equal to rho cosine phi, so that means that the cosine of phi is equal to z over rho. And so this is going to be minus 2. We know z is minus 2 from up there, and rho is 4. So we get minus 1/2. And now we have to not specify just cosine of phi, though. We have to use the inverse cosine. And we know that the inverse cosine of minus 1/2 is 2 pi over 3. Similarly, we know from our equations that x is equal to rho sine phi cosine theta, but this time we're going after cosine theta, and we already know what phi is, so we can substitute those things in, and we will get that this is equal to 0, because we know that the x is 0. Well, the inverse cosine of 0 is pi over 2, so we know theta is pi over 2. So that means that the spherical coordinates then are going to be rho. It is going to be rho theta phi, and so that is going to be 4 pi over 2 and 2 pi over 3. Now, you should be warned that a lot of times, especially in your physics courses, they will reverse the meanings of some of these variables, in particular theta and phi, and sometimes they'll use r in place of what we call rho. So just be mindful of that when you look at different books or when you take different courses. But the concept is the same. There are many applications to the sciences. Let's talk about them. Because many surfaces can be written as functions more easily described either in cylindrical coordinates or spherical coordinates for that matter than they can be written in rectangular coordinates. As examples, air traffic controllers use radar systems that work with cylindrical requirements. The value of a rho and theta give the horizontal distance and angle of a plane from the control tower, and the value of z gives the plane's elevation. Programmers of global positioning systems, that is GPS systems, can use spherical coordinates to express locations. Elevation is associated with rho, longitude is associated with theta, and latitude is associated with phi. And finally, for now, celestial coordinate systems are used to monitor positions of stars relative to a particular point. Astronomers use such systems expressed in spherical coordinates with rho as the distance from the center and theta and phi as angles from two planes. A lot of times people will call this right ascension and declination to describe these sort of celestial longitude and latitude metrics. Now let's turn our attention to evaluating triple integrals with spherical coordinates. In the spherical coordinate system, the counterpart of a rectangular box is a spherical wedge, and you can see a spherical wedge over here. And that is a set described as E, and this is going to be rho theta phi, where rho is between two numbers A and B, theta is in between two numbers alpha and beta, and phi is between two numbers here called C and D. Although we define triple integrals by dividing solids into small boxes, it can be shown that dividing a solid into small spherical wedges always gives the same result. Just take that as a given. We're not going to invest time doing that now. So we divide E, this E, into small spherical wedges by means of equally spaced spheres. Rho equal rho sub I, half planes theta equal theta sub I, and half cones phi equal phi sub k. I guess this is I, j, and k because they can be different. And so we can find the approximate value of this spherical wedge this way. Now it turns out that this side here is the change in rho. So you're just talking about going out. Rho extends, so that's a delta rho. And the other side is going to be rho sub I delta phi. And that's if phi changes, and so you get rho sub I delta phi. And then you're going to be multiplying that by rho sub I. And actually, I think what I'm going to do is, you should really spend some time understanding this, and I think I'm going to blow it up just a little bit so you can see it perhaps clearer than this figure shows it. Okay, so here we blow it up. Okay, so what happens is you have a slice up here, and we're going to say that this is approximately, even though this is a spherical wedge, this is approximately the volume is length times width times height, approximately. So here what happens is I'm going out, and this is getting this is a little wedge, so rho goes from rho, and then there's this side is then delta rho. Now if I fix rho and just let phi go, this side becomes, so this is rho, this is delta rho. Now this side right here is the only thing that's changing for fixed rho is phi. So this is rho delta phi. And this other side, which is down here, is a little bit harder to see. But what happens is this is delta theta. So what you really can do is you can, and you want to spend some time understanding this, but you see, if you think about this being phi, this is the r distance here. So that really is what is rotating there. So this side is at a distance of r, which is rho sine phi delta theta. Spend some time making this thing your own. But what we're going to say is the change in volume is approximately length times width times height. And when we take the limit, it is going to be dv is going to be rho squared sine phi d phi d theta d rho. Okay, so that's pretty much what we're doing here. So the little rectangle, spherical rectangle that we have, its volume is approximately this, and we add up all of these little spherical pieces, and take the limit as n goes to infinity to get the triple integral. But we do remember that this ends up being a Riemann sum for a function capital F, which is this, and now it's a function of rho, theta, and phi, which really is the f that we started with way up here to integrate sine phi, cosine theta, and so on and so forth. And that's what we have. And notice that the volume element comes along with, and so dV ends up being represented in this way also. It is the rho squared sine phi, and I guess I really even cut it off a little bit, and then it'd be d rho, d theta, d phi whenever we integrate. I guess I'll say that again here. Actually, I'm going to say it better here. So this is the formula that we'll have for triple integrals in spherical coordinates. So the integral is going to be this expression. Notice that we made the change of variable for x, y, and z here. Our limits are in terms of those variables of integration, and to accomplish the change in volume from this transformation, dV becomes rho squared sine phi, d rho, d phi, d theta. This is really just when we, in polar coordinates, this is the same thing as r, except it's not really just r, but it's the same concept. dA became r, dr, d theta, and so dV becomes rho squared sine phi, d rho, d theta, d phi. And this is what the spherical wedge is. Now this formula says that we convert a triple integral from a rectangular by introducing these and by using the appropriate limits of integration, and we replace dV by rho squared sine phi, d rho, d phi, d theta. Let's move ahead and really try to do a problem. So the problem that I'm going to ask you to do is this one down here. You want to evaluate the triple integral over b. This is e raised to the x squared plus y squared plus z squared whole to the 3/2 dv. And b is the unit ball, and here's the definition of b. It is x, y, z such that x squared plus y squared plus z squared is less or equal to 1. You know what to do. Let's see how you did. Okay, well, we're going to make note that x squared plus y squared plus z squared is equal to rho squared. And b is, in fact, the whole unit disk. So rho is going from 0 to 1. Theta is going from 0 to 2 pi. And phi is going from 0 to pi. So this integral becomes this iterated integral. Just doing direct substitution, and notice that I put dv to be rho squared sine phi, d rho, d phi, d rho squared sine phi, and then it is d rho, d theta, d phi. And this is an integrated, and by the way, in the same way that you often in polar coordinates integrate first with respect to r, it is often the case that you'll integrate first with respect to rho here. And in fact, this is one of those things where this is a very simple integrated integral, because you see you have parts of this that are functions only of rho, namely this part of it that's only functions of theta, this part, and part of it that's only functions of phi. So you can break it apart this way. You can't always do this, but you can in this case. So you compute this integral and multiply them together. And so we compute them, multiply them together, and we get 4 over 3 pi parentheses e minus 1. Make sure you understand this calculation. And it's worth realizing that it would have been very difficult to evaluate this integral in rectangular coordinates. It would look like this. Here's another problem for you to do. Use spherical coordinates to find the volume of the solid that lies above the cone, z equal x squared plus y squared, square root of that, and below the sphere, x squared plus y squared plus z squared equals z. So this is the picture that we've drawn here, and I could ask you to sketch the picture yourself, but I'm letting you benefit from this picture now because we're focusing on the other thing. So we want to be evaluating the volume of this shaded area. You know what to do. See how you did. Okay, now notice that sphere that we were talking about there has radius 1 and it has a center at 0, 0, 1/2. So you see that means we can take this expression, and x squared plus y squared plus z squared really is just rho squared, and z is rho cosine phi. So we can divide both sides by rho since it's greater than 0, and so rho is equal to cosine phi. And the equation of the cone, which is the square root of x squared plus y squared, can be written as, and there's z. So z is rho cosine phi, and I can put in x squared and y squared, and I can simplify this by factoring out the rho squared sine squared phi, and then I get cosine squared plus sine squared, which is 1, and so this is rho sine phi. So that's the equation of the cone. So this gives us, and if we just look at this, so we have rho cosine phi equal rho sine phi. So that means that the only time those two are equal in the area, in the domain rather of phi is for phi equal pi over 4. And so therefore we now have worked very hard on the geometry here, and we have that E is rho theta phi. Theta goes from 0 to 2 pi. Phi is going to go from 0 to pi over 4. Okay, so you see phi goes this way, so it's 0 to pi over 4. We go all the way around, though, to pick up all the area. And rho goes from 0 to cosine phi is what it is on the boundary of the sphere. So that's the setup of the integral. So let's do the calculation of the integral then. The volume of that is going to be the integral of 1 dv. Now remember that the units don't match well, but actually this is going to give you numerically the volume. And so we put in those values. Now notice that here we are going to do d rho, d phi, and d theta. So that means when we're doing rho, what's going to happen is that rho is going to go from 0 to cosine of phi. So those are the limits here. So I integrate rho squared and I get rho cubed over 3, and I plug in those values before I move to the next integral. So then I have this integral that I'm going to, and whenever I plug in those values and simplify, I get this. And now what I'm going to do is I'm going to evaluate this integral. Again, you can let u equal cosine cubed. You get cosine to the 4th over 4 minus that, and you have constants, and this is pi over 4, and that is 0. So you plug in the numbers, do the calculation, and you get pi over 8. Make sure you understand this calculation. Again, there's many times when you'll use this. Astrophysicists can estimate the mass of a star by calculating the triple integral of its density function in spherical coordinates. Since the star is approximately spherical, the integral bounds in spherical coordinates are constants. A geologist could calculate the average density within a particular region of the Earth by using a triple integral in spherical coordinates. The region can be approximated using a portion of a spherical wedge. And a factory manager can determine the amount of rubber required to make the shape of a hollow sphere, which is really what a tennis ball is, using integrals and spherical coordinates. Since the ball is in the shape of a sphere, its outer surface and inner surface are easily represented in spherical coordinates. Before we finish this, I'd like for you to do another problem. Find the volume of the solid that lies between the sphere shown here, x squared plus y squared plus z squared equals 16, above the xy plane, and below the cone z equal x squared plus y squared square root of that. You know what to do. Let's see how you did. So we think about the drawing over here, and we are going to use many of the same substitutions that we used in the earlier problem. And so what we're going to learn this time, it's a little bit different since we're centered at the origin. But when we look at the sphere, we're going to know that this sphere has radius 4, so that is rho equal 4. Rho goes from 0 to 4. And z is equal to the square root of x squared plus y squared, and that tells us that, and we work through it. And again, in exactly the same calculation we did before, we're going to get that theta is equal to pi over 4. Now in this case, we're finding the volume that lies within the sphere, above the xy plane but below the cone. So we're going to go from phi is going to go from pi over 4 to pi over 2. Okay, so let's put it all together then. So this is the integrals and the limits that we have. Here's another picture of that. You can see that what we're finding the volume of. So the volume is going to be the triple integral dv. These are the limits that we talked about. That's a 4. That's and then we have to change dv to rho squared sine phi d rho d phi d theta. Actually, d theta d phi is the way I have it here. We integrate first with respect to rho, and actually in this case again, there are separable functions. There are factors that are phi, theta, and rho only, so I can take the product of those, and if I do this correctly, I get 64 square root of 2 pi over 3. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.